Welcome to this explainer on the 2026 MATE ROV competition for the Ranger class. We're going to be looking at an absolutely incredible challenge today. This is where student entrepreneurs literally step into the shoes of global innovators, and they're tackling real-world, highly complex, harsh environment challenges using underwater robotics. Whether you're a seasoned robotics enthusiast or just, fascinated by ocean engineering, this breakdown is going to show you exactly how the engineers of tomorrow are being tested right now, today.
Okay, let's jump right in with a really powerful quote from the competition manual that basically anchors this entire mission. It says, "Equipped with scientific data, we can proactively and confidently move from the ocean we have to the ocean we want." And that's key, right? The core objective here isn't just to build a cool robot. It's about taking those technical skills and transforming them into actionable real-world solutions. Because in this competition, these student teams aren't just students. They function as full-blown startup companies tasked with creating a healthier, more sustainable ocean.
So, here's our mission briefing map for today. We'll be running through 1. Science in harsh environments. 2. Mission 1. Cold water corals. 3. Mission 2. Tracking icebergs. 4. Mission 3. Offshore wind power. 5. Mission 4. Under ice floats. And finally, 6. Building tomorrow's workforce.
Section 1. Science in harsh environments, pushing performance.
For the 2026 World Championship, we're heading to the renowned marine facilities in St. John's, Newfoundland and Labrador. Now, this place is a massive global hub for ocean technology. Here, ROVs, that's remotely operated vehicles for those newer to the space, are tested in the Marine Institute's massive flume tank as well as the National Research Council's 90-meter indoor ice tank, which, by the way, is essentially just a giant, freezing indoor ocean. The whole point of this environment is to prove a very simple concept. If your team's robot can work here, in these brutal, highly controlled simulated conditions, it's going to work absolutely anywhere.
Section 2. Mission 1. Cold water corals, seabed 2030.
Our first expedition stop plunges us straight into the Funk Island deep. Now, before mapping the seabed here, we need to talk about photogrammetry. It's a critical tool these student startups are required to use. Basically, they have to create a highly detailed 3D model of the underwater environment, but they only have their ROV's standard two-dimensional cameras to do it. So they have to carefully maneuver around a target, snap a bunch of photos, and use software to stitch them all together into a 3D model.
Take a look at the sheer density of these rare cold water corals from the actual Funk Island Deep Marine Refuge. It's almost like a giant, living puzzle. They're so densely packed that researchers literally can't even see the seafloor underneath them. And that is exactly why accurate 3D mapping and the super delicate collection of these species is absolutely vital for our conservation efforts.
So to pull off this first task, teams have to execute a series of very specific steps inside that simulated flume tank we talked about. First, they have to gently collect basket stars and coral species. But here's the catch: they can't damage them. That means they have to grab the substrate, which is the rocky base the corals sit on, not the fragile coral itself. Then, they build that scaled 3D photogrammetry model, and finally, they have to fly a really precise transect line over the coral garden. Oh, and did I mention they have to do all this while fighting a strong, persistent underwater current? Yeah, it's intense.
All right, Section 3, Mission 2, Tracking Icebergs, Smart Atlantic Alliance.
We're leaving the debriefs now and transitioning to the extremely perilous waters off the coast. The real-world stakes here are just massive. Picture this. On one side, you have these towering, totally unpredictable icebergs. On the other side, multi-billion-dollar offshore oil platforms. A collision between a staggering 350-kiloton iceberg and vital offshore infrastructure, well, that would be completely catastrophic for both human life and the surrounding environment.
So for this task, the ROV basically acts as the ultimate underwater scout. Teams are given a map of 4 major platforms in the area: Hibernia, Terra Nova, Hebron, and Sea Rose. They have to calculate the exact threat level to these platforms by pulling some very specific data parameters. They need to locate the iceberg, determine its heading, and crucially, they have to measure its keel depth underwater to within a staggering 10 centimeters of accuracy.
But measuring icebergs? That's just the start. Mission 2 is incredibly dense. It demands that competitors execute a huge array of tasks in the exact same run. They'll need to count invasive European green crabs using image recognition, simulate an acoustic release to, actually, scratch that. It's simulating a release to rescue whale-safe fishing gear, like a submerged lobster pot. And then they have to perform delicate subsea maintenance by replacing an eDNA sensor on an observatory, which tracks genetic material in the water to monitor biodiversity. Talk about the ultimate test of a multi-purpose robotic system.
Next up, Section 4, Mission 3, Offshore Wind Power, Scalable Energy Solutions.
For our third stop, we're shifting our focus to the future of power. We're looking at how to unlock global energy needs by connecting floating offshore wind farms directly to existing subsea infrastructure. But before heavy construction even starts, teams have to mitigate environmental impact. So the big concept here is deploying a bubble curtain. Securing those floating wind turbines involves driving massive anchors, called micropiles, deep into the seafloor. And as you can imagine, that is incredibly noisy and highly dangerous to marine life. A bubble curtain solves this by pumping compressed air into submerged rings, creating a literal wall of bubbles that absorbs all that dangerous sound energy.
Teams are going to simulate this scalable energy model in the offshore engineering basin tank. It's a really delicate balancing act. Operators are carefully juggling heavy, industrial underwater construction with very strict environmental stewardship, ensuring the local ecosystems aren't harmed while we pursue clean energy.
The precision required here is completely off the charts. First, they have to successfully place the bubble curtain right over the target zone. Then, they have to carefully thread the micropile down through that active moving bubble curtain into its designated spot. Finally, they basically become underwater electricians. They have to retrieve a subsea power connector from the wind farm, safely lay the cable through a designated waypoint, and plug it directly into the oil platform's port to deliver power.
Which brings us to Section 5. Mission 4, Under Ice Floats, MATE Floats.
For our final expedition stop, we're actually leaving the ROV behind entirely. We are plunging into freezing temperatures to design and deploy independent, vertical robotic profiling floats under polar ice sheets. This is all inspired by the real-world GO-BGC project. Scientists are currently deploying a massive network of 500 robotic profiling floats all over the globe to monitor ocean chemistry and health. And the students are challenged to join this effort by designing their own custom vertical floats. Now, operating in polar waters, it is a logistical nightmare. Out in the real world and simulated right here in the NRC ice tank at a brutal negative 25 degrees Celsius, you've got solid, impenetrable ice above you. If a team's autonomous float tries to surface while it's still trapped under an ice sheet, its delicate sensors are just going to get crushed against the ice and destroyed. So these floats have to be engineered with internal memory and really smart ice avoidance capabilities, meaning they delay any data transmission until they are fully and safely recovered.
So how is this actually scored? Well, a team's custom-built buoyancy engine has to flawlessly hit some exact depth markers. It descends to exactly 2.5 meters and just holds there for 30 seconds. Then it ascends to exactly 40 centimeters, hovering just below the ice, and holds again without touching the surface. They have to repeat that entire profile a second time. And here's the kicker. Only after the float is physically recovered from the freezing water is it allowed to autonomously transmit its plotted data graph back to the mission station.
Finally, Section 6, Building Tomorrow's Workforce, the Entrepreneurial Startup. Let's step back for a second and look at what tying all these extreme missions together really means. Why simulate coral mapping, iceberg tracking, and under-ice robotics? Well, because these students aren't just building robots. They are functioning as real-world startup companies. They are developing critical thinking, teamwork, business acumen, and high-level project management. These are the exact real-world employability skills that the global workforce so desperately needs right now to solve the climate and engineering challenges of tomorrow. And they have to prove it all. Through mandatory technical documentation, high-stakes engineering presentations to a panel, and flawless product demonstrations under intense pressure, these teams have to prove to the judges that their tech can truly handle the harshest environments on the planet. Because that motto really does hold true. If it works here, it's going to work anywhere. And so, I'll leave you with this final thought as we wrap up this look at these incredibly complex blueprints and ambitious goals. The ocean is waiting. Will this next generation of engineers build the technology to actually save it? Thank you so much for joining me on this explainer today, and we'll see you next time.